Let me share the screen. Is my screen visible? Please respond.
Yes, sir. Yes, sir.
Okay. So once again, welcome to the problem solving session for the sixth week for the course of Geotechnical Engineering 1 offered by Professor D.N. Singh uh, of Department of Civil Engineering of IIT Bombay. And I am Yogendra Narayanan. I am a second year PMRF research scholar who is a teaching assistant for this course and who will be conducting these problem solving sessions every week on Saturdays 5 p.m. to 7 p.m. So precisely these sessions are to make the learners proficient in the concepts that have been covered in the corresponding week by solving some numerical questions or uh, conceptual questions from the earlier uh, uh, earlier available assignment and examination question papers. So that the learners will be accustomed to the type of questions the uh, and the various approaches to solve the problems. And to give a brief account of what has been covered in the previous week, that is sixth week of the lecture, is essentially the compaction characteristics of the soil. Uh, so why compaction is done, what are the objectives of doing compaction, and what are all the type of laboratory compaction tests, and how followed by how it is achieved in the field by various uh, compact compact compacting techniques and vehicles are by several means, and followed by the factors affecting the and essentially the analysis of compaction characteristic curve, the terminologies of maximum dry density and optimum moisture content, and followed by the factors affecting the compaction characteristics and how the compaction characteristics affect some of the soil properties. So with this, the this was the essentially the week that was covered, and also this week we'll be starting slightly in one step backward. So we'll be solving one or two problems from the concept of effective stresses also, since it is a very it is one of the most important concepts of geotechnical engineering. So we'll be starting with two problems in effective stresses and followed by the problems on compaction characteristics. So uh, I would like the learners to be uh, uh, who are all attending to be responsive uh, and actively solve problems along with this. And if you have any doubt, you are very welcome to intervene in the middle and interrupt me in the middle, and uh, I I will be clarifying your queries. So do not hesitate to ask your doubts. This is essentially to make your concepts clear. So with this, we will move to the first question. Hope my screen is visible. Can you just confirm?
Yes, sir. Yes, sir.
Okay. Now we'll start with the first question. It is on effective stresses. So let me read out the question. If the groundwater table lowers from 2 meters to 4 meters, what will be the change in effective stress at a point 6 meter below the ground level? Will it increase or decrease from the previous condition? Assume dry unit weight as 16 kilonewton per meter cube and submerged unit weight as 10 kilonewton per meter cube. So first of all, in this type of questions, it is always better to draw a figure. Uh, can you solve it or you need assist? Can you solve and say the answer?
Sir, I saw.
Okay, you solve. Meanwhile, I will also. Uh, you are undergraduate student or what is your background?
Sir, undergraduate.
Which year?
So third year.
Okay, okay. From which institute?
Sir, from SSM college. It is in Kashmir.
Okay, okay. Can solve the question. So always draw figure first. So there are two conditions. This is the ground level. So initially the water table was at 2 meters. Now it has gone deep to 4 meters. We have to calculate the stress at 6 meters.
So I think A option.
Yeah. This is at 6 meters. So what will be the effective stress for this condition? 16 into 2 plus 10 into 4 will be 32 plus 40, 72 kilopascal. And for this condition, it will be 16 into 4 plus 10 into 2 will be 64 plus 20, 84. It is A or B?
So I think A.
How did you calculate? Are you able to see the calculations here?
Yes, sir.
So initially this is the groundwater table. At this condition, the dry here it will be 16 and here it will be gamma submerged will be gamma submerged is gamma saturated minus gamma W. So directly if you multiply it with the depth, you will directly get the effective stresses.
Yes, sir.
So 16 into 2, it will be 32 plus 10
10
into 4 will be 40,
50 plus.
it will be 72. So now in this case, the water table has lowered. So in this, you can assume the ideal condition that when it is lowered, the depth will be uh, that portion will become dry. So this whole portion will be 16 and this will be 2 meters. That you should note that 6 meter below ground level. So it will be 16 into 4 plus 10 into 2 will be 16 fours are 64 plus 20, 84. Are you able to understand?
Yes, sir. Yes, sir.
So it will be 12 kilonewton increase. Where did you go wrong?
Sir, in second part, I go wrong.
Okay. So uh, this will be 12 kilonewton per meter square. It will be increase. Now are you able to get it?
Yes, sir.
Okay, let us move to the next question. So, a layer of clay extends from the ground level up to a depth of 6 meters and overlies a 6-meter thick sand layer. The water table is at 6 meter from the ground level. The unit weights are given, and a surcharge load of 50 kilonewton per meter square is acting on the ground level for a long duration. So you have to calculate the effective stress at 3 meters, 4 water pressure at 6 meters, total stress at 6 meters, 4 water pressure at 12 meters, and effective stress at 12 meters. So can you
Sir,
solve it?
what is surcharge load?
Okay, let me explain. So first let us draw the layer of the soil that is given, right? Now this is the ground level. So what they have given is a layer of clay extends from the ground level up to a depth of 6 meters and overlays a thick sand layer. So this will be clay, this will be sand, because the layer of sand, it is given as the layer of clay overlays the sand layer. So it will be 6 meters and it will be 6 meters, and the water table is at 6 meters. So this is at the interface. Now, unit weights are 20 kilonewton per meter cube and 16 kilonewton per meter cube. Now, what is meant by surcharge? The definition of surcharge is semi-infinite loading. That is, whatever area is there, there will be a uniform loading. It is, have you come across uniformly distributed load?
Yes, sir.
So it is similar to that, uniformly distributed load.
Yes, sir.
That is known as surcharge.
Okay, sir.
So it is a constant surcharge of 15 kilonewton per meter square or kilopascal
Yes, sir.
acting on the ground level. So now you first calculate the effect. How to, first question is effective stress at 3 meter below the ground level.
Yes, sir.
So what will be the answer here? Sigma dash at 3 meters will be, how much it will be?
One second.
This is
I think 48 megapascal.
here you have to note that
Yes, sir.
this 50 kilonewton is there, right?
Yes, sir.
See, when uh, now if you draw the total stress diagram, what will be the stress at ground level?
So no idea.
Surcharge is acting, right? So it will
Yes.
be 50 kilonewton at ground level,
Yes.
50 kPa. So when you need at 3 meters, for consider, let us consider 3 meters. So it will be, you have to add 50 plus 16
16.
into 3. So it will be 98
Okay.
kilopascal. Always surcharge will be added to the total stress. And wherever you are calculating, you have to add the surcharge uh, as it is,
Yes, sir.
right? Now you calculate C. Let us for pressure. Let us do it afterwards. You calculate C. Question C. Total stress at 6 meters.
It is 15 plus 16 into 6. 146.
Hmm. So it will be 50 plus 16 into 6. It will be 50 plus 96. It is 146. Now you calculate B and D.
What happened? Water pressure and 6 meters below ground level. So I think 140.
No, pore water pressure at 6 meters from ground level. This only pore water pressure. So water table is here. That
Yes,
is,
sir.
water is exposed to atmosphere.
Yes, sir.
So pore water pressure will be UW at 6 meters will be how much? Be 0, since it is subjected to atmospheric pressure. All right. Surcharge will not play any role on it.
Okay, sir.
Okay.
Yes, sir.
Now you calculate D, pore water pressure at 12 meters.
Sir, 140.
Will be 12 meters, right? Here it will be 0, and if you multiply it, this is pore water pressure is gamma W into Z. How much you are getting? 9.81 or 10 into this is 6.
6. 918.
You will get approximately 58 around. Are you getting it?
Sir, why we multiply 9.81?
See, how are you calculating total stress here? You are multiplying density of soil with depth, right?
Depth.
Gamma into Z.
Yes, sir.
Same. Uh, See, when what is Pascal's law? With depth, what will happen? The water pressure will be
Oh,
gamma W into Z
depth.
in the
Yes, sir.
same manner. Water pressure will increase.
Yes, sir. Yes. Point six.
Are you getting?
Yes, sir.
So you calculate the D last question. So you have to combine all the concepts here to calculate it. So how much it will be? Sigma dash at 12 meters will be first. What are all the total stresses? 50 plus 16 into 6
6.
plus 20 into 6. This will be the total stress. Core water pressure will be 9.81 into
Into 6.
6.
Yes.
You get a 146, 266. You get approximately 208 or something.
201.14.
207.14. This is the effective stress. Are you getting?
Yes, sir.
Now you are able to understand how surcharge is taken into account.
Yes, sir. Yes, sir. It is
And
added up to the depth of water table.
hmm, and so now you can solve with variable groundwater and different surcharge or any uh, these type of problems. So
Okay.
you can go through the last week lecture. In the same manner, we have solved some problems, including the effect of capillarity.
Yes, sir.
So that part uh, you can get accustomed with. So these concepts, why I am doing it again is it is one of the most important uh, concepts which will be coming uh, hereafter in both this course and the following course of geotechnical engineering too. And another aspect is from the point of gate also, uh, focus will be more on these type of questions. So in that way also you can get the familiarity of concepts. Now let us move to the next question. Calculate the maximum dry unit weight of a soil mass having a voids ratio of 0.7 and G equal to 2.65 if the optimum moisture content is 17%. Can you solve it?
Sir, 20 seconds.
How much?
Sir, 1 minute, 1 minute.
Okay, okay, okay. Carry on.
Sir, I got 7.80.
Uh, did you use this relation?
Yes, sir. Same relation.
So how much is gamma W? Can take
Sir, it is 9.81.
9.81.
Yes, sir.
G is 2.65.
2.65.
So wide ratio is how much you are getting?
D option. 15.3.
3, that if you use it as pen, you will get 15.6. That is not an issue.
Yes, sir.
It will be 15.6.
6.
Yeah. Now, uh, let us move to the next question. So, in a standard Proctor test, weight of the hammer is considered as 3 kilograms instead of 2.6 kg, and the number of compaction layers are 5 instead of 3. What will be the new compaction energy transferred to the soil? Can you solve it, or am I audible?
Yes, sir. Yes, sir.
Can you solve it, or you need us?
Sir, a little bit hint needed.
Okay. So what will be the energy that is applied to the uh, your while compaction you are applying energy, right?
Yes, sir.
So how that energy can be calculated? It will be the potential energy.
Potential energy. Yes.
Potential energy will be
Mg.
mg
H. H.
h. How much
Uh,
time you are doing it? You are giving 25 blows.
yes, sir. 25.
And how many layers? Either it is 3 or
3.
it is 5. Now, in standard Proctor test, height of fall will be 31 centimeters.
Yes, sir.
Alright. So now you substitute here 3 into G is 9.81 to H is 0.31. Convert into meter. 25 into 5.
Option B.
So it is simply the potential energy formula. So this is for one blows. That is sorry, one blow. You are giving 25 blows and you are doing it for either 3 or 5 layers. So you will be multiplying it. So the option will be B. That is 1140 kilojoule per meter cube. Right. So
Yes.
next question. Out of the following methodologies, which one is used for compacting coarse grain soils?
Sir, D. Vibrations.
Yes, that is right. So where uh, static compaction are used?
Sir, I think saturated soils.
Yes, and mostly static compaction. It is how to put it. So we'll be using it mostly in laboratory for sample preparations. So in that way, you will be using static compaction, where you will be using sheep foot rollers.
Sir, where whites are more.
So sheep foot rollers, it is more suitable for clays. And falling weights, this case is more suitable for deep compaction. Mostly cohesive soils are compacted by falling weights and sheep foot rollers. Deep compaction means if you are to compact uh, more layers of soil, it is a sort of ground improvement also. And vibrations are for coarse grain soil. And there is a one more technique uh, that is associated with vibrations for improving coarse grain soil. Can you think of it?
Sir, repeat the question.
So for coarse grain soils, there is one more way which is similar to vibrations, uh, which can be used to uh, use for compacting. That is large areas. So this can be achieved by blasting also. right?
Okay,
So
sir.
for coarse grain soils, blasting can also be used. And let us move to the next question. So who has joined the call, you can start solving from the present question. And the slides and the video will be uploaded in your NPTEL interface. So you can have a look. Mostly it will be uploaded today or tomorrow. And you can, I think you can all access those links. So
Yes.
select the desired objectives of compaction. Why compaction is being done?
So B, C, sir, B and C are correct, but about A, no idea.
Mr. Krishna Kumar, you have raised your hands. So do you have any queries? Please respond. Okay. So you are saying that it is used for, you are saying B and C are correct, right? Right. So what does compaction do first? So you know the compaction characteristics. With what you will plot the characteristic curve? What will be in the x-axis?
Sir, water content.
Water content, right? And y-axis?
Gamma dry.
Gamma dry. So by compaction you are getting a curve like this, right? So your what is the aim of compacting it? You are trying to attain this part, right? That is, what is this known as? Maximum dry density, or gamma d max.
Yes, sir.
So when density increases, what happens to the strength of the soil?
So increases.
So one of the ways why compaction is being done is to it results in the increase in its density, which will increase its shear strength. This is also right. And when density is increasing, E will reduce, porosity will reduce, hence permeability will reduce. See, B is also right. Settlement is, since the air voids are removed, further volumetric change under these circumstances cannot occur. So ultimately, settlement also will be decreased. So the option is all the above.
Sir, what are the reasons of settlement?
Settlement, see, why settlement is caused?
I think improper ground surface.
Ground surface, it is essentially, what is that? It is volumetric deformation,
Yes, sir.
right? So volumetric deformation means volume of voids are decreasing because volume of solids will remain constant. They cannot change. Now volume of void should decrease. When you compact it, the uh, volume of voids corresponding to air voids will decrease. All right.
Yes, sir.
So under if you are applying at the end of compaction, when you are achieving maximum dry density, there will be no more air voids that can be released by application of load, and whatever the load we will apply further during the construction or something, it will be comparable to that of the load that you have applied during the compaction process. So there will not be further reduction in volume. So that is why it will decrease the settlement also. Are you clear now?
Yes, sir. Clear.
And this is a instantaneous
Yes,
phenomena.
sir.
Now when you introduce time, when the permeability is very less, then it will then that phenomena will be very different. It is known as consolidation, which we will be studying in the further classes. So now we no need to go into consolidation. Uh, so this is compaction. Compaction, always remember, compaction is expulsion of air voids only,
Yes, sir.
only air voids. So obviously the option will be all the above.
Yes, sir.
Okay. Now the figure represents compaction characteristics of two soils A and B. So what type of soil B, what type of curve that soil B will be, uh, uh, how to put it? What type of soil B is assigned to a particular soil? Which type of soil will exhibit this type of behavior?
Clay soil.
Okay. So let us go one step behind. So one step back. So what does soil B, that curve, signifies? What is the physical significance of it?
So it represents density after compaction.
Yes, both curves
Yes, sir.
depicts density versus moisture content. So how do you you know that the density of soil A is lesser than density of soil B, and you have two type of curves. So what will you infer from this? Okay, let me explain it. So this curve, let us consider these curves. All right. So let us consider this moisture content. So this is having a lower density and this is having a relatively higher density. All right.
Yes, sir.
So now let us consider this water content. Now this is having relatively lower and this is having higher. All right.
Yes, sir.
Now, water content, difference in water content is same for both the cases, right? What about density here? Which is having higher change in density?
Soil A.
Soil A is having higher change in density. All right.
Yes. Yes, sir.
So what does that mean? Soil A is more compactable
Then soil B.
than soil B. That is, when you are applying, even though you are applying force, or even though you are applying energy, the density of soil B is not at all increasing.
Yes.
Increasing in the sense, not at all increasing in the sense, not significant increase. So, what does that signify? That particular soil is very difficult to compact. You are
Compact.
unable to achieve the higher density with it.
Yes, sir.
That usually you will be encountering in extremely clay soil and extremely sandy soil.
So clay soils.
Both clay soil and extremely sandy soils are also very difficult to compact.
Yes.
And what about A? Which type of soil will depict?
Soil.
Will be mostly a combination of that is a well graded soil, combination of silts, clays, and small amount of sands. They will exhibit typical bell shaped curve.
Bell shape curve.
So now, are you able to understand the physical significance of the different compaction curves?
Yes, sir. Yes, sir. Got it.
So when you are given a figure, always try to understand what does it signify. What does it physically signify? If there is a change in density, what does this soil undergo? So that part you have to think about it. Then that is the way you have to analyze these graphs,
Okay, sir.
right? Let us move to the next question.
सर
So
गुड इवनिंग सर।
yes, yes, tell me.
सर बोले कि तो असाइनमेंट नंबर 5 में सर वीक वीक नंबर 5 में सर क्वेश्चन नंबर 9 का आंसर 0 होगा या 20 होगा सर।
Which
इफेक्टिव
assignment?
एजुकेशन
Which assignment? Present assignment or previous assignments?
प्रीवियस असाइनमेंट असाइनमेंट नंबर 9 सर सर 5 सर असाइनमेंट नंबर 5 वीक 5 सर।
No, no. अ, आप किसके बात कर रहे हैं? अभी जो असाइनमेंट रिलीज हुआ है उसमें बात कर रहे हो या क्या है?
जिसका सर सॉल्यूशन आ चुका है सर असाइनमेंट नंबर 5।
अच्छा, वो अ, उसका इधर हम डिस्कस नहीं करते हैं। वो आस्क अ क्वेश्चन नाम से एक टैब है ना, उसमें क्वेश्चन लिख दीजिए, वो आंसर करेंगे।
सर मतलब पीछे प्रीवियस वाला भी असाइनमेंट में क्वेश्चन गलत था वाटर कंटेंट निकालने का, तो उसमें
वो
वेटेज 0 दे दिया था लेकिन इसमें अभी तक दिया नहीं है।
नहीं नहीं, आप समझ लीजिए, ये सेशन वो असाइनमेंट क्वेश्चंस डिस्कशन के लिए नहीं है।
यस सर। ओके सर।
वो ये सब आपको जो इस वीक में पढ़ा हुआ जो कॉन्सेप्ट्स कवर हुआ है उसके प्रैक्टिस करने के लिए है। जो असाइनमेंट्स आपने जो क्वेरीज है आपका, वो आप वो आस्क क्वेश्चन नाम से एक टैब होगा एनपीटेल आपके अकाउंट पे, उसमें लिख के सबमिट कर दीजिए। वो जो टीए है वो आंसर करेंगे आपको।
यस सर।
ठीक है।
थैंक यू सर।
हाँ,
ठीक है।
अभी ये सब प्रॉब्लम सॉल्व करना है तो ये सिर्फ इसी के लिए है ये सेशन। उसमें कृपया वो उसका आर्ग्यूमेंट मत लीजिएगा। ठीक है।
ओके ओके
हाँ
सर।
हाँ, क्योंकि इसका इस सेशन का पर्पस अलग है।
यस सर।
ठीक है, अभी लेट अस मूव टू द नेक्स्ट क्वेश्चन। सो so if moisture, that is optimum moisture content Proctor, gamma dry Proctor, and represents the maximum dry densities and optimum moisture contents obtained by performing Proctor and modified Proctor test. What is the correct relation between these parameters? Can you answer this?
Sir, option B.
Check once again. Option B or D?
Sir, B. Second.
No, no, check once again. Okay. Just this part you just answer. So, in which type of Proctor test you will apply more energy?
Sir, modified.
Modified, you will apply more energy, right?
Yes, sir.
Now, if you are applying more energy, what should happen to the dry density?
Sir, decrease.
No, no. When you are applying more energy for a particular water content,
Yes, sir.
what will happen to the density?
Increase.
It will increase.
Yes, sir.
So, gamma dry of modified Proctor will be more. All right.
Yes, sir.
So that is these two options coincide. Now another condition is moisture content. So at what moisture content? Now it is better to draw the curve. So let us assume that this is for standard Proctor, right? What will happen to modified Proctor? How it will shift?
Sir, it will be lower than this.
No, no. Modified is you will be applying more energy. So the dry unit weight will increase,
Increase. Okay, sir.
and this curve will shift left upwards. So optimum moisture content will decrease. Gamma D will increase. All right. Energy in modified Proctor will be greater than energy in
Proctor.
standard Proctor. That is Proctor compound.
No, sir.
So hence gamma dry of modified Proctor will be higher. Moisture content of modified Proctor will be lower. Now you can let me put it in this way. You will be understanding. See, first you are mixing, for example, 5% water. All right.
Yes, sir. Yes, sir.
Now you are applying some, for example, you are applying, let us say 1000 joules energy, 1000 kilojoules. All right, you will attain a particular density. So let us say standard Proctor confines to 1000 kilojoules. Not exactly, it will not be 1000 kilojoules for a argument's sake. All right.
Okay, sir.
Now, what happens to modified? It will be almost 2000. Let us say 2500. It will be more than that, significantly more than that. All right.
Yes, sir.
So, at the 5% moisture content, what will be the density? This, when you apply this much energy, obviously soil will compact more. So, its density will be higher. And the moisture content at which it attains the maximum dry density, that also you will be getting lower, because at a relative, if you are getting gamma d max of standard Proctor at 10%, you will get this gamma d max of modified Proctor at 5% or 6% itself.
Yes, sir.
So option C is right. Optimum moisture content of Proctor will be greater than optimum moisture content of modified Proctor. So always remember this curve. All right. Standard Proctor, modified Proctor. It will shift to left upward sides.
Okay, sir.
So you no need to remember everything. If you know this graph, you can understand what is happening here. All right.
Okay, sir.
Now let us move to the next question. So this is the condition. You have to match AB with both IJ and XY. Can you answer this?
Sir, 1 minute.
Okay.
Sir, A will be I. Dry of optimum. It is core of the dam.
Okay.
Sir, wet of optimum. Sorry, wet of
Uh,
optimum. It is core of the
okay.
dam.
Okay. It will be B I. Then
Sir, then it is Y.
okay. Good. Then for A,
Sir, it is J and X.
yes. So this part obviously you know, core of the dam and embankment. So when dry of optimum is there, this is the applied stresses, and this is the volumetric deformation, that is E. So what happens at lower stresses? It will be like this. It will be dry It will be wet. And for higher stresses, the curve will be like this. This is dry, this is wet. Are you able to get?
Sir, please explain X part more. Less deformation at low stresses.
Yes. So this is for lower stresses,
Yes, sir.
and this is for higher
Low
stresses.
stresses.
Now X part is right at dry off optimum. Dry
Yes, sir.
off optimum, see, this is initial. You consider it as initial condition. All right. Uh, if you take this as sigma 1, and initially both are at a void ratio E1. All right.
Yes, sir.
Now you consider at a particular another sigma. This is sigma 2. This will be, let us say, E2W, and let us say E2 dry. Now what does deformation mean? Essentially it means E2 minus E1, right?
Yes, sir.
E is void ratio. So change in voids ratio is obviously deformation.
Deformation.
Now compare the magnitude of E2D minus E1 and E2W minus E1. Which is more?
Sir, E2W minus E1.
Yes, obviously this is greater than this one. So at lower stresses, what is happening? It will undergo, dry is undergoing lesser volumetric deformation. All right.
Yes, sir. Got it.
So when you come for higher stresses, obviously you know its slope is more, its slope is relatively less. So this time dry part will undergo, dry of optimum will undergo more deformation. So that is why wet of optimum will go less deformation at higher stresses. Dry of optimum will undergo less deformation at lower stresses. So this is the exact match of answers.
Yes, sir.
Are you clear, or you are having any more questions?
No, sir. Clear.
My way of explaining is all right, right?
Yes, sir. Yes, sir. Great.
Okay. Then let us move to the next question. What will happen to the capillarity if the soil is compacted? Sorry, soil is compacted more. Just ignore this. It's been a typing mistake.
So B option.
Yes. Why it will increase?
Sir, because water pressure increase, water table goes on up.
That part actually, capillarity does not depend on water pressure. So see, let us consider two cases, right? You are having water in two what to say, two containers, right? Okay.
Yes, sir. Yes, sir.
Now you immerse a capillary tube of this much diameter, let us say D1, and another tube, introduce a thinner capillary tube of diameter D2. So how much will be the capillary rise in first case? Let us consider this as case A and this as case B. Which will have a more capillary rise?
So A part.
No. Capillary rise will be more when the diameter is smaller. HC is inversely proportional to D.
Okay, sir.
Right? Now, same. When as you consider this capillary tube as voids of the soil. Now, how will be the case here? The soil will be arranged like this, and you consider water table here. This is initial condition. Now soil is getting compacted, means they are closely arranged. Air voids are getting exposed, grains are rearranging, it, but water table is same here. You are able to get the analogy?
Yes, sir. Yes, sir.
Now in which case capillary will be more?
So A part.
No, no, see, same. This B corresponds to this one.
Yes, sir.
This A corresponds to this one. So this will have, B will have more capillary rise. It will rise, for example, this much, but here it will be this much.
Sir, but if we compact it more,
Uh,
how the water will rise above it?
yes. Now, what will happen to the pore size here?
So which point?
In the soil, when you compact it, what happens to the pore size?
Sir, it will decrease.
Decrease. Then, if you apply this relation, what happens to the rise in capillary?
Increases.
Yes, that is what is exactly happening. Compaction, you are compacting the soil such that you are decreasing the pores,
Pores. Yes, sir.
and as a result of it, it will be the capillary rise will be more in compacted soil.
Okay, sir. Got it.
Yeah, so uh, compaction of soil increases, that is, it facilitates capillarity.
Yes, sir.
All right. So let us move to the next question. A soil sample, you can solve this question. I will be right back in a minute. Sorry for the inconvenience. I will be
Okay,
right
sir.
back in a minute. You can
Okay, sir.
solve this question. Are you able to solve it? That is, are you getting idea to solve it?
So little idea needed.
Okay. Did you solve it?
So what will be the saturation?
For which question you are asking?
So first S-while sample compacted.
No, no, that is fine. You are solving which part?
So first part, dry unit weight.
That does not require any saturation, right? Okay. What is the formula for relationship for gamma dry?
Gamma
Gamma dry
W into G.
plus W.
Yes, sir.
This is the gamma dry that you get at OMC. See, there are two conditions you have to understand here. This actually most people will get confused here. So this is the compaction curve, right? And
Yes.
this is what? This line is known as
Zero line.
zero air void line.
Yes, sir.
ZA VL. So now there can be two cases here. So this is the maximum dry density that you achieve by compaction, right?
Yes, sir.
What will be the second case? Here the saturation may not be 100%, but theoretically you should achieve this much, which is not possible. So this gamma d is what you are achieving. So that will follow this relation, right?
Yes, sir.
And dry unit weight at 0 air voids line will follow this relationship. Gamma Wg plus 1 plus E. In this case, SE equal to Wg. S is 1, and you can solve by 1 plus Wg. Are you able to get it? Now, this first part, you need to get it with this. This part, you have to get it with this. Always this will be greater than this one. All right.
Yes, sir.
So you can solve this and let me know the answer. Then we will know how this saturated unit weight is calculated.
Sir, in first case, it is gamma d is equal to gamma water.
No, this is bulk, gamma bulk, that
Gamma
is given here, 2.06. Here we did not give dry density, we have given density. So it is bulk density.
1.80.
Yes, 1.807.
Yes, sir.
1.807. What is the unit? Gram per cc. Always say with unit. Please don't forget to put the units. And you calculate this part, second part, dry unit weight at 0 air voids.
Sir, it is 18.015
18 unit.
gram per cc.
Oh, it will not be 18. What gamma W? Gamma W you should not use 9.81. When you use it as
1.
9.81, it is
1 G
kilonewton.
per cc.
It is be 1
Yes, sir.
into 2.67 divided by 1 plus 0.
1.836.
Yes, it will be 1.836.
Yes, sir.
Now the last part is little tricky. So if the voids become filled with water, what would be its saturated unit weight? Right. Now this is the maximum dry density that you are achieving,
Yes, sir.
1.807. So at that density, soil is saturated or not?
No, sir.
It is not saturated. because if it is saturated, it will be touching zero air voids line,
Zero air voids. Yes,
and
sir.
no compaction curve will touch zero air void line. It is impossible to attain 100% saturation at maximum dry density.
Mount dry density. Yes, sir.
All right. So that means volume of voids will be already some water is present and some air is present. All right.
Yes, sir.
Now, what will remain constant? Vs will remain constant.
Yes, sir. Volume of solids.
Volume of solids is weight of solids
Those solids.
by density of
Density of solids.
solid. Now you know this, what to say, uh, gamma dry. Gamma dry is known as, gamma dry will follow weight of solids by total volume.
Total volume.
Right. You take it as 1 cc. Let us consider volume we are taking it as 1 cc. All right.
Yes, sir.
Now uh, now we have to find Vs. So you know that 1.807 gamma S, how will you compute? Gamma W into G.
E.
How much you are getting? Gamma W you use as 1.
0.676.
Yes, approximately 0.68.
Yes, sir.
So that means, so what is the volume of voids here? Total we are considering 1 minus Vs. So it will be 1 minus 0.68. It will be
0.32.
0.32 cc.
Yes, sir.
Now this is the volume of voids.
Voids.
Now what for saturation, whole weight of water should be 0.32.
Yes, sir.
All right.
Yes, sir.
Now gamma dry is there. Now what will happen, that you have 0.32 cc void space, and now already some water is there. All right.
Yes, sir.
Now 14% water. So what is the moisture content formula? Water content is equal to weight of water by weight of solids.
Solids.
So this is 14%, 0.14 into weight of solids is 1.807. How much is weight of water?
0.252.
0.252. That means total voids is 0.32 and already present is
252.
0.252. All
Yes,
right.
sir.
Now how much water you need to add?
Minus 0.32.
It will be 0.068.
0.68. Yes, sir.
All right. Now this much water you are adding. So this is how you calculate how much water is to be added. Now you have to calculate saturated unit weight. Saturated gamma sat is equal to weight of solids, that is total weight
Total
of soil mass by total volume.
volume.
Now what will be the total weight here? 1.807 plus 0.252, which you are already adding, already present, and 0.068. How much you are getting?
So 2.127.
2.127. And what is the volume? Obviously, we are considering it as 1 cc.
1 cc.
So what will be the gamma sat here?
2.127
2.127 gram
divided
per
cc.
cc. Are you able to get now?
Yes, sir. Yes, sir.
So this is the final answer. Shall we move to the next question?
Yes, sir.
Okay. This is just a straightforward answer which we have discussed already. A bell-shaped Proctor compaction curve implies which kind of grading?
Well graded.
Well graded. So it will be well graded. Will be well graded. Let us move to the. Let us solve one problem here. All right, similar to that. Okay.
Yes, sir.
So just look at this problem. The following data are given in connection with the construction of embankment. Soil from burrow pit. That is, let me just explain the preface of the problem. So there are two conditions here. All right. Now this is the destination and this is the source. Okay.
Yes, sir.
Now you have to at destination you have to achieve this condition.
Okay, sir.
For that you are burrow, that is you are excavating a material from burrow pit which is having this property.
Yes, sir.
Are you now that is you have source and
Source.
destination.
Yes, sir.
What is the density here? This will go here,
Yes, sir.
this will go here.
Yes, sir.
All right. Now for every 100-meter cube of compacted soil, okay, that is at destination, for every 100-meter cube of compacted soil, here volume is 100
Meter cube.
meter cube.
Yes, sir.
Quantity of soil to be excavated from the burrow pit, here how much you have to excavate? All right.
Yes, sir.
Now you have here bulk density, you have moisture content, you have volume, one part you have, another part you need to find out.
Yes, sir.
Now here which parameter remains constant? See, now dry density, not natural density of burrow pit is different,
Yes, sir.
water content is different. volume will be obviously different, right?
Yes, sir.
What is the composition of volume? Vs plus V, right?
Yes, sir.
Now this will not change,
Change.
and correspondingly, even though this changes, its mass will not change, that is weight will not change.
Okay, sir.
So the constant value that is present here is weight of
Solids.
solids, right? So that you need to calculate. That how will you calculate?
Moisture content. So weight of water upon moisture content.
Okay. Now you have bulk density here, right?
Yes, sir.
So what is bulk density?
Mass by volume.
So you need weight of solids. You
Yes,
know
sir.
volume. Which is the component that relates weight of solids and volume?
Weight of solids.
Gamma dry.
Dry.
Weight of solids by total volume. This you know 100. This you need to find out. And gamma d, you know that gamma by 1 plus
1 plus E.
W.
W.
Yes. This gamma you know it as 2 megagram per meter cube. And water content you know as 0.18. Now you can calculate Ws. Are you able to understand now?
Yes, sir. Yes, sir. 169.4
Yes. Into megagram,
megagram.
right?
Yes,
This
sir.
is 169.4. Now you know this one. Now this is going to remain constant,
Yes, sir.
right? Now you have to uh, calculate uh, how much amount of solids you have to get it from
Borrow bit.
borrowed pit.
Yes, sir.
Volume will remain for, let us consider here also I made a small mistake. This also is 100 meter cube. All right.
Yes, sir.
Now you know this part. Now you have to incorporate both moisture content and natural. You have to take into account the density also. How will you calculate here? You have to calculate the how do I put it now? You know this weight, all right?
Yes, sir.
169.4. Obviously you can divide by 100 or whatever the unit is. You need uh, this will be, you need total weight, right? Will be 1 plus W.
W.
How much you are getting? Here, what W you will be substituting?
0.12.
Yes, it is for burrow pit. So you have to substitute 0.12.
189.72.
Yes. So quantity of soil excavated is 189.72 megagrams. That is 189 tons. So now coming to the second question. What is the amount of water to be added? Now this is remaining constant, right?
Yes, sir.
So what is water content?
Weight of solid
Weight of water,
water upon
weight of solids.
solids.
So extra difference in water content will be Ws into W2 minus
U1.
W1, which will be Ws, 169.4 into 0.18 minus 0.12.
Sir, why we consider here difference?
Because amount of water to be added.
Yes, sir.
So what is the moisture? To attain this moisture content, how much water you are going to add?
It's 10.16
Tons. It will be 10.16 megagrams or tons.
tons.
So this is how embankment calculations, and now uh, now you are able to get the how it is done.
Yes,
Now same concept, we will be solving one more real life problem, right?
yes, sir.
Now you note this problem. An embankment fill needs 700,000 meter cube of soil with a void ratio 0.7. There are two burrow pits, X and Y, from where the required soil can be taken and transported to the site. Right. Now the conditions for burrow pit is given. It is 0.75 and another burrow pit is 1.65. All right. And for whatever, for 1 meter cube of soil you are excavating, the transportation charge is 20
20.
rupees, and
Yes,
the
sir.
second is 15 rupees.
Yes, sir.
So if you take soil from pit X, burrow pit X, what will be the charge transportation cost for the entire soil mass? Now what you need to find? Now you can classify it as X and Y. All right. And the destination, you need to have a void ratio of 0.7 and total volume is, this case is how much? 7 into
7
10 power 5
power 5.
meter cube.
Yes, sir.
And you need to calculate V here and V here. You know E is 0.75, E is 1.65. Now, which is the common parameter relating it?
So E.
That is true. Which is which common parameter which that is relating does not change? Vs will not change, right?
Yes, sir.
We are dealing with volumes. Here, volume of solids will not change. So, first you need to calculate volume of solids. How can you calculate volume of solids in uh, for first you calculate for x volume of solids for x. If you calculate, how much you are getting, you can calculate 0.75 is equal to volume of voids by volume of solids, one total volume minus Vs
Yes.
by Vs, and when you V is
7
7
10.
lakh, E is sorry E will be 0.7 because you are calculating volume of uh, destination. So you calculate with 0.7 because this volume we don't know. This and this we need to find out. All right.
Yes, sir.
So how much you are getting Vs?
Four one one seven.
Yes, that is right. Now you know total volume of solids.
Yes, sir.
Now with the same formula, you calculate volume that is needed for X and volume needed for Y. Now what you know? Vs you know, V you don't know, E you know for both the cases. You can calculate Vx and Vy.
Yes, sir.
This is Vx and this is Vy.
720 for VX.
Okay.
Point 65 minus 417. 4797.
Okay. Now you calculate the cost.
144
Yes, for x.
x.
Second,
719.
15 it is.
If
Yes, that is true. Correct. Okay.
yes, sir.
Now you are able to understand now?
Yes, sir. Yes, sir.
Okay. Let us solve one last problem and we will close this session. This is a relatively easy problem. So, the maximum and minimum dry densities of a sand are determined in the laboratory to be 1682 kilogram per meter cube and 1510 kilogram per meter cube respectively. In the field, that is, they have given the relative density as 70%. Now they are asking to calculate the dry density and relative compaction. Now first you calculate dry density. Relative density is equal to 1 by gamma min minus 1 by gamma d divided by, sorry, and 1 by gamma d minimum minus 1 by gamma d maximum. How much you are getting? 0.7 is equal to 1 by 1510 minus 1 by gamma d divided by 1 by 1510 minus 682. How much you are getting?
Sixteen point two eight.
Okay. 16.28. You say in this kilogram per meter cube.
Yes, sir.
How much you are getting?
16.28.
16. You
Yes,
should
sir.
get in 1600s, na?
Sir, 1628.66.
1628.66
Point six six.
kilogram per meter cube. Now this is the dry density you achieved in field, right? Now
Yes.
what is known as relative compaction? This is gamma D in field, gamma D max in laboratory. What is gamma D max in laboratory?
So 1682.
1682. Field it is 1628. Now calculate what is relative compaction.
Point 0.96.
It is 96%.
Yes, sir.
So dry density is done, relative compaction is done. Now calculate the bulk density if moisture content is 12%. You know gamma bulk is equal to gamma D into 1 plus W. 1628 into 1 plus 0.12. How much you are getting?
Sir, 1824.09
Okay,
kg per meter.
1824 kg per meter cube.
Meter cube.
So this is how it is done. Right.
Yes, sir.
Now, since some 5 minutes is left, last only one problem we will solve. So others are relatively uh, uh, straightforward questions. So you can, when once the slide is uploaded, you can go through those questions and try it yourself. And if you have any confusions, you can ask in the next session. All right.
Sir, where are the slides are uploaded?
Okay. Now you have your NPTEL portal, right?
Yes, sir.
In that, there is a in the left side you have the tab of weekly contents, everything.
Yes, sir.
At the end you will have problem solving session January 2024.
Yes, sir. Yes, sir.
If you go there, it will direct you to a Google Drive link,
Yes, sir.
and if you click that, you will find all these video links as well as slides.
Okay, sir. Okay.
Okay.
Yes, sir.
Now let us solve this question quickly. Ratio of energy imparted to the soil sample in case of standard Proctor to modified Proctor. So now in this case you have to remember some aspects here. So standard Proctor, let me give those specifications. Standard Proctor and modified Proctor. You can also note down this because it is a code, IS code.
Okay, sir.
So you need to remember these values. So in standard, energy.
Yes, sir.
Energy imparted is weight, that is m into g into height
Yes, sir.
into number of blows
Number of blows.
into layers.
Layers.
Now, what are all the things you need to know? Weight of the hammer you need to know, height of fall you need to know, blows you need to know, and layers you need to know. Now, for standard Proctor, mass of uh, that is the weight of hammer will be 2.6 kg, and for modified it will be
9
4.9
kg.
kg.
Yes, sir.
Height will be 31 centimeters, height will be 45 centimeters. Number of blows will remain 25,
Yes, sir.
This is also 25. Layers will be 3,
And
in this
5.
case 5. Now you calculate energy ratio. ER is equal to 2.6 into 9.81 into 0.31
P1
into
25
25 into
3
3 divided by
4.9
4.9 into 9.81
1.45
into
25.
0.45 into 25 into 5. This will cancel. This will cancel. This will be approximately, it will be 2 by 3,
0.219.
0.219. Right. This will be the energy ratio.
Yes, sir.
219, right?
Yes, sir. Sir, but it means कि standard Proctor is
Less
more,
energy.
is equal to 0.219 modified Proctor energy.
Yes.
Yes, sir.
So
Yes, sir. Yes, I got it.
now you understand why modified Proctor energy is more.
Yes, sir. Yes, I got it.
Okay.
Yes, sir.
These parts, these two slides are remaining. This you can go through. These are
Okay.
simple questions, simple formula substitution.
Okay, sir.
You will be able to solve it. Given that we have discussed a lot, I think today. So
Yes.
I hope you understood these concepts now.
Yes, sir.
So with this, we can conclude this session. And year afterwards, the concepts will be more important. And if you want to learn this subject, you I would suggest you to attend these sessions for more concept clarity. And it will be on Saturdays, every Saturday, 5 to 7 every week.
Okay, sir. Thank you, sir.
Okay, let us meet
Okay, sir.
next week.
Okay, sir. Thank you.
Okay,
Okay, sir.
thank you.